All right, welcome back, and we're talking today about how we actually strengthen materials, ways we can modify a metal to be stronger. Now you go back and just refresh our memories here. Elastic deformation, remember, is stretching of primary bonds or secondary bonds. If we're talking polymers, those will be involved as well. But we're just talking about the stretching between the atoms, the bonds between the atoms or the molecules. And remember, plastic deformation is due to primarily due to slip of dislocations. And so you remember we have a block of crystal, we apply a shear stress to that. You're going to pop in a dislocation eventually if the stress is high enough and oriented properly. And then that dislocation can propagate through the crystal. And at the end of the day, we have a slip step. The crystal has been distorted, and yet we've only broken one bond at a time. So slip is the key. It's the most common way that plastic deformation occurs. Now, also remember, we can have twinning, and just this is another nice illustration of the twinning situation. Elastic deformation will distort the bonds in a structure. Dislocation slip will cause a slip plane to develop, okay, but the actual structures internally will not be affected by this. We'll just have the slip boundary that is shifted, but everything else in the two blocks is the same. But twinning actually changes the angles in all elements of the block. So it's in general, a higher energy mechanism than a dislocation slip, and more difficult to do. And so in a lot of materials, it doesn't occur because slip occurs first. All right, so those are your elastic and plastic deformation reviewed. Now remember, slip happens on slip systems. That is, dislocations only move in close packed directions in close packed planes. And that means all possible planes and all possible directions in a material are not available for slip, for dislocations to move. So when we think about the actual yield behavior in a polycrystalline material, we find that it's a little more complicated than simply reaching the desired, the required shear stress in an ideally oriented crystal. So if we look at the center grain, the arrows represent the direction of the preferred slip plane. Obviously, there's more than one, but let's just imagine we have one is all oriented. And so if that is oriented at 45 degrees to the applied far field normal stress, then that's kind of the optimum orientation to get maximum shear stress on this plane. So this crystal should want to slip at a much lower global stress than crystals that have less favorable orientation. So as soon as this outside stress is big enough, this crystal should slip. However, if it's going to slip, it's to change shape, and the neighboring crystals, they're not ready to slip, they're not going to allow it to change shape. So you get a reinforcing effect, and so what we find is that polycrystal materials, by their nature, even if they're fairly large crystals, will have higher yield strength than monocrystals because of this interference or reinforcing effect that occurs. Crystals are not free to slip whenever they reach the desired or required stress. They have to do so cooperatively with neighboring grains. Now, when we look at plasticity or the deformation of the crystalline metals by dislocation slip, we find that we get a lot more deformation than you would expect if you just took all of the pre-existing dislocations, everything that was in the crystal when we started, and from that you can kind of estimate how much deformation you should get. Well, we get a lot more than that. In fact, if we use X-ray, we can measure the dislocation density, and that increases during plastic deformation. So obviously we've got to be making some dislocations, but it's even worse than that, because most pre-existing dislocations, not all, there are some alloys where pre-existing dislocations will break loose and can move, but in most cases pre-existing dislocations are pinned by atmospheres of impurities that keep them from moving, so they can't contribute to the slip that we observe. The conclusion is obvious: dislocations are going to be created in any plastically deforming material. Now, there's two ways to make new things. There's homogeneous nucleation. And in homogeneous nucleation, we simply have the required shear stress at the required angle to cause a dislocation to form. And that's homogeneous because the conditions are the same everywhere. Nothing assists. Heterogeneous nucleation will occur if something is raising the local stress. So you may have a large inclusion, a void, a defect of some kind, something that creates a higher stress locally, which favors formation of a dislocation. And so we then will see dislocation formation around that defect. Now, just to give you a sense of how crazy these can be, there's what's called a Frank Reed source. And a Frank Reed source is a factory for making dislocations. And it consists of at least 3 dislocations, 2 that are oriented in a vertical plane in such a way that they interfere with a third, which you can think of as a crossbar here of these goalposts. And the shear stress acting on this crossbar, and the crossbar is like a half plane, a curtain hanging down, is going to tend to make that dislocation slide from right to left. But the ends are pinned because of these other dislocations that hold the ends. So if we look down from on top, what's going to happen is as we apply shear stress, this dislocation is going to grow, it's going to balloon out. We're going to generate a ring of dislocations. And this line is a curtain of extra half planes hanging down into the page. And you say, well, this is really crazy. But here's an electron, transmission electron micrograph of a Frank Reed source at work. There's a boundary going on here that gives it the funny squared off corners. But the point here is you see everything we're talking about, the loops forming, blowing up, all right? And this then is an extra half plane. Each of these represents, you're looking down on an extra half plane of atoms that grow down into the material. And this is generating dislocations. And you might think of dislocations as like quanta or packets of deformation. And once you make them, then you can move them around, or they get moved around in the crystal. And so a Frank Reed source is a factory for making dislocation lines and whatever that can be then shifted around. Now, so when we think about how do we prevent the formation and the movement of dislocations, it's really helpful, I think, to think of by analogy and recognize that dislocation movement occurs on these slip systems, and let's think of those slip systems as freeways on which dislocations move. So if you take that analogy, you think about what messes up traffic on a highway, you've got 3 major categories of things. The freeway can be blocked because of construction, can be cut entirely. You could have way too many cars. That happens at rush hour. Even though there's nothing broken down or not even anybody going slow, the presence of a lot of cars will shift slow traffic. And then, of course, you can have pedestrians, stopped cars, breakdowns, accidents, whatever, that also slow traffic. So what are the analogies here? Well, freeway construction, where you just block the road entirely, is really analogous to grain boundaries. Dislocations don't jump grain boundaries in general. They have limited ability to do that. And so as we refine the grains of a material, as we add grain boundaries and make the grains smaller by refinement, we are going to interfere with dislocations, and in doing so, we're going to make the material stronger. We're going to resist dislocation movement. Now, you can think of it a couple of ways. One of the ways is to think in terms of a large crystal structure versus a small crystal structure. If I want to produce a single slip step in the top image, I only have to make 3 dislocations and propagate them through 3 crystals. If I want to do the same thing in the finer structure, I have to make 8. Now, every dislocation involves raising the energy of the crystals. Here I have 3 dislocations. I have to put in that much work to raise the energy of those crystals. Here I have 8 dislocations, so you have to put in energy to create 8 dislocations. In both cases, you're getting a single dislocation step out of the process. So the distance that your force you're applying is going to act is the same in both cases. But if I have to do more work over the same distance, then this is going to require a higher force to get the same effect. So greater strength because more grains need dislocations. So you can think about that as an energy concept. Now we see with grain size changing that the yield strength goes up. And so we've plotted here the negative of the square root of the diameter. So, the reciprocal of the square root of the diameter. That means as the diameter is getting smaller, this number is getting larger. So as we go left to right, we're talking smaller and smaller grains Obviously, the limit out here would be a single grain. Okay, so it'd be like a left edge limit, and that makes sense. We've got a very large grain. And so we see a pretty dramatic increase in this particular metal. It's rising, yield strength rising from about 5 KSI, 4 KSI, to well over 30, and over that range of grain sizes. All right, next analogy, too many cars. It turns out in slip, we're going to have a limitation that dislocations can't share space. They interfere with each other. And this is called work hardening, or sometimes called strain hardening. Both those terms are common. And all that happens is as we add dislocations, we're going to find the material stronger and stronger. So what you see is as we increase the density of dislocations, and again, this would be measured with something like X-ray diffraction or some other technique. Even with different grain sizes, and this is not a huge difference or huge range in grain sizes, but we see that the increase in density of dislocations increases the yield strength, the stress required to cause permanent deformation of the material. You're going to have homework about this, and we'll do some problems with this in class, applying some of the rules for strain hardening and predicting the resulting yield strength. So in general, it turns out that the effect of dislocation density isn't really monotonic. If you go down to 0 dislocations, it turns out the material will actually be quite strong. But as the dislocation density increases a little bit, we're going to see a drop in the strength. And then over the normal range that we find in engineering materials, we'll see in general an increase in strength with dislocation density. Okay? So it's not simple. If you could make an absolutely perfect material, adding dislocations would actually weaken it. But once you get to enough that you can shuffle them around, adding a whole lot really shuts things down and raises the strength again. All right, the third thing that shuts things down is pedestrians, stopped cars, what have you. And basically, these are barriers to movement. And there are several ways we could do this. Your book separates this into 3. I like to lump them together because in terms of basic mechanism, they're similar. They're going to be a foreign body, not part of the host material, host metal or host structure, that interferes with dislocation movement. And so there could be alloying elements where the atoms distort the crystal lattice and make it more difficult for dislocations to move. We could have alloying elements that, as the part ages, they precipitate out of solution and will form small collections of maybe dozens of atoms or small, very small groups of atoms, not large particles. These are very small. We call those precipitation-hardened alloys. And precipitation hardening is really neat. It's very elegant, but it can be difficult to control the final size of the precipitates. It's very sensitive to thermal history and to age. And so if you want very, very consistent barriers to movement, you want very consistent hardening particles, then it's common to do what's called dispersion. You pre-make the particles that you want to add, and then you just mix them in, and they never are in solution, so you don't have to worry about their size varying much. So alloying elements, we're putting in individual atoms, precipitates, small collections of atoms that precipitate out of the material after it's fabricated. And in dispersions, we put in particles of a chosen size, and we specify and prepare them. And we find carbon, of course, is the perfect model for this. You've already seen this once, and I told you we'd see it again. This is very important that you have a general sense of what's going on. As we add carbon, your Rockwell hardness rises, and it reaches saturation. Now, why does it do that? Because after you get to a certain level of carbon, almost all of the unit cells are going to be distorted by that carbon that really doesn't fit very well into the structure of iron. And that distortion is going to make dislocation movement very difficult. And adding additional carbon doesn't fundamentally change that difficulty because everything's already distorted at that point. So that's the saturation point that we get. Now, we can see this also with solid solution strengthening. So here's copper. Looking at the tensile strength as a function of weight percent nickel. And yield strength follows a similar kind of deal. So this is your ultimate tensile, and here's your yield. And you see, running from 220 to over 400, so almost a doubling of strength as you go to 50% nickel. And so these are substitutional alloys, but that's why we do substitutional alloys. Strengthens the material. Because though nickel's a good substitute, it's not a perfect substitute. And because it's not a perfect substitute, it does distort the lattice of the copper just a little bit and makes dislocation movement more difficult. Okay. So that's how we strengthen materials. Now what happens if we take a metal that has been plastically deformed? So we've put a bunch of dislocations into it, we've shuffled those around, and if you reheat it to a high enough temperature where diffusion becomes significant, where you start to have a lot of diffusion, you're going to get a series of steps. The first step is called recovery, and in recovery, the dislocations are eliminated, and they're eliminated by diffusion, and we'll look at how that happens. Then you're going to get recrystallization. Because the grains that you are working with are high energy, generally they've been distorted because of all the slipping that's gone on. New grains are going to form that are equiaxed, that are perfect, they don't have dislocations in them, and they're going to form between and within the old grains. And then as we continue to heat, those equiaxed grains that have formed are going to grow, gradually absorbing all the old distorted grains and then continuing to grow because that minimizes the free energy of the system as you have fewer large grains. So what does this look like? Well, when we do this, we're going to reverse the effects of the working or the cold working we've done on the material. Tensile strength, which was raised by cold working, is going to drop. Ductility and toughness, which are reduced by the cold working, are going to rise as we heat over some time period. So this is actually, we're looking here at annealing temperatures, not really time, but you get a similar effect if you hold a given temperature and hold for a length of time. The point is we're going to restore original properties. So what does this look like? Well, recovery is going to result from diffusion, most commonly. And so we have two dislocations here, top and bottom, extra half planes. And if atoms will diffuse here in the middle, the energy of the entire system is going to be dramatically lowered. So when atoms do that, they reduce the whole energy of the system. So this is a very stable place, and that diffusion will generally not be reversed. Atoms are not going to jump back out of this. And those dislocations are annihilated. So that's the kind of thing that's going on in recovery. For recrystallization, we're going to actually form new grains. So here is a distorted material, 33% cold work brass. If we start to reheat it, now 580 is a very high temperature, almost immediately you're going to get nucleation of new crystals. And so you see these little particles forming, new crystals forming on the boundaries. And as we continue to heat, you're going to get these new crystals consuming all the old grains until they're all gone. Now, this is happening very rapidly because of the temperature being used. If we then continue to cook this long enough, you're going to get large grains that consume the smaller ones. And of course, this happens because we're going down the energy slope. This is a much lower energy microstructure than the one on the left. Because these are large grains, we don't have nearly as much grain surface, and so more of the atoms are in a perfect neighborhood. Okay? So that's the grain growth that consumes the old distorted grains. Now, because strength is easily modified, I want you to learn some values for strength, but they're not single values for given materials. Even if we were to pick a particular steel, say a 1018, the range of strengths possible with a 1018 is huge. So what I want you to learn, and these will be quiz questions, is you need to know the range of strengths that are likely or easily achieved for the three common materials that we did modulus for: steel, aluminum, and polycarbonate. Now these are ranges, and so when students will ask, well, what's the strength of 2024 aluminum? And then the answer is, well, I don't know. There's a range. It's between 10 and about 40 or 50 KSI. It won't go as high as 70. But it depends on what you've done to it and what its history is, how it's been cold worked, or if it hasn't been cold worked, and so on. And it depends on the grain structure. So you need to know ranges. 50 to 200 KSI for steels, 10 to 70 for aluminum, and 6.5 to 10 KSI for polycarbonate. And I think we'll call it quits there. Our next lecture will be looking at the mechanisms by which things fail and fracture. And so look forward to seeing you there.